For our performance final, we will be doing 2 experiments to test 2 laws of physics. For our first experiment, we will be using 3 balls of differing masses, all dropped at the same height. This experiment is meant to test Galileo's law of falling bodies. From the data collected, we will create a displacement versus time graph and an energy versus displacement graph. In the first experiment, the independent variable is the mass of the ball, and the dependent variable is the time that the ball takes to reach the ground. For our second experiment, we will be using 3 balls of the same mass and dropping them at different heights on a yardstick. This experiment will test the law of conservation of energy, since we will be creating an energy versus displacement graph to see the changes in kinetic and potential energy over time. In this experiment, the independent variable will be the height, and the dependent variable will be the time to reach the ground, which also affects the velocity, therefore affecting the energy.
So for our setup, we have a yardstick, which is measured in inches, so we will have to convert that to meters. We also have a golf ball with a mass of 0.046 kilograms, a tennis ball with a mass of 0.058 kilograms, and a soccer ball with a mass of 0.43 kilograms. We will take turns dropping the different balls from the 36-inch mark 3 times and time it to see if they drop at the same speed to test Galileo's law of falling bodies. We will also calculate the energies of the balls at the different heights using the potential energy formula mass times gravity times height and the kinetic energy formula of 1/2 mv squared. To find the velocity, we will use the kinematics equation. Velocity equals initial velocity plus acceleration times time. We will graph the displacement v time graph using the average time for each ball from the 3 trials, and if it's not linear, we will linearize it. We will also graph the energy v distance graph and use a straight line for the potential energy and a dotted line for the kinetic energy, and we will do the same for all 3 balls. For the kinematics equation, we will use the average time for each ball from the 3 trials as we did before. Again, if it's not linear, we will linearize it. For our second experiment, we will drop the tennis ball 3 times each from the 36, 24, and 12-inch mark, and we will convert those into meters in our equations and graphs. From this, we want to see the relationship and ratio between height and energy. We will graph the energy v distance graph and use a straight line for the potential energy and a dotted line for the kinetic energy for the balls from the different heights. And now we will go on to the trials.
Here's the data that we collected for our displacement versus time graphs for the 3 balls of differing masses. We collected the time that it takes for each of these balls to reach certain points along the meter stick. We chose 36 inches, 24 inches, and 12 inches. We then converted this into meters, and we recorded the time that it took the ball to reach each one of these marks. The values collected in this displacement versus time table required no calculations, since we simply used the timer to time how long it took them to get to a certain point along the meter stick. Now shown are the graphs created using the data from the displacement versus time tables. Since the relationship between the displacement and time is exponential, we took the square root of the displacement for each of these graphs to linearize them. On both the linearized and non-linearized versions of the displacement versus time graphs, displacement measured in meters is plotted on the y-axis, while time measured in seconds is plotted on the x-axis.
To calculate the percent error, I used the second calculated time for each ball. So starting with the golf ball, I used the time of 0.3 seconds, and I used the formula v squared equals v naught squared plus 2a delta x, and I compared that to my experimental value and got a percent error of 20.5%. For the tennis ball, I used the measured time of 0.288 seconds, and using the same kinematics formula, I got a percent error of 15.7%. Finally, for the soccer ball, I used the time of 0.294 seconds, and once again, with the percent error formula, I got a percent error of 18.7%. Also, because we were measuring displacement in our displacement v time graph, back in the percent error formulas, when we were calculating for time to see the theoretical versus experimental, time is distance over velocity, so instead of using displacement, we use distance. Some potential sources of the error include miscalculation of the timer. So even though we are using a stopwatch, there is that reaction time which can account for a miscalculation in timing. Another possible source of error could be air resistance. Even though we were indoors, there's still that air resistance that could influence the time it takes to reach the bottom. Some ways we can improve this would be possibly having an automated timer that pauses once it hears a sound. So once the ball hit the ground, it would pause, similar to clap-on lights. Another possible solution could be trying to neglect air resistance as much as possible. I'm sure there are some scientific laboratories that have negligible air resistance rooms. Some limitations from being constrained to household materials and measuring devices is the fact that we had to use a yardstick instead of a meter stick because none of us had a meter stick, so we had to do all those calculations into meters. Another limitation is the lack of balls that we could use. We only found about 3 balls in the house. We actually only found 2. I had to go back to my house and bring one, so we could not extend the experiment to 5, say, or 6 balls. For this, the time is the independent variable and the displacement is a dependent variable, and as the time increases, the displacement also increases, so it's a direct relationship.
Now shown is a table containing the values used to construct the energy versus height graph. Height, time, potential energy, and kinetic energy were all needed to construct this graph. Height was used to calculate the potential energy by using the equation mgh equals potential energy. Time was used to calculate the velocity, and this velocity was then used to calculate the kinetic energy. A sample of the work that was done to find both the potential and the kinetic energy is now shown. As seen, the kinematic equation V equals V naught plus AT was used to calculate the velocity of the ball at different times. This velocity was then plugged into the formula 1/2 mv squared to calculate the kinetic energy. These kinetic and potential energies were then used to create an energy versus height graph, with energy in joules being on the y-axis and height in meters being on the x-axis.
As you can see from the graph, the potential energy and the height are directly related. So, as the height increases, the potential energy also increases. However, the kinetic energy and height have an indirect relationship, so as the height increases, the kinetic energy decreases. Now shown is the percent error for the 3 different balls at the same height for the energy V height graph. So to find the percent error, we use the initial potential energy and the final kinetic energy. As stated in the law of conservation of energy, the initial potential energy should be equal to the final kinetic energy, and the initial potential energy formula is mgh. So that formula should be correct as we already know the mass, gravity, and height. What we are testing to see if we got right was the kinetic energy, because it includes velocity, which we use time to calculate, and time is an imperfect value, so that could have had an influence on our kinetic energy and increased our percent error. For the golf ball, we got a percent error of 0.971%. For the tennis ball, we got a percent error of 4.62, and for the soccer ball, we got a percent error of 1.82. Once again, some potential sources of this error are the miscalculations in timing, especially with the larger percent errors, as our stopwatches are not perfect. Another source could be possibly air resistance, which could have an influence on the energies and gravity. Some ways we could improve the experimental design to reduce errors is possibly doing more trials to get a more average time. The source of our error is a difference in velocity, which comes from an incorrect time or a miscalculated time. So doing more trials would give us a more accurate time. Some limitations experienced due to being constrained to only household materials, as stated before, include having to use a yardstick instead of a meter stick, which led to a lot of conversions from inches into meters. Another limitation was the lack of possible balls we could use. We only could use 3. We couldn't test this out on things with much larger masses like bowling balls, because 1, we could damage something, and 2, we didn't have access to it. Finally, the relationship between our independent variable mass and our dependent variable energy is that as the mass increases, the energy also increases.
To further test the law of conservation of energy, the kinetic and potential energies of balls dropped from differing heights were then tested. A table containing all of the values used for this graph uses the time taken, potential energy, and kinetic energy, much like the graph before, but now uses a ratio of the current height to the total height. At a ratio of 1, the ball would be at the highest possible height. For example, if the ball was being dropped from 36 inches, it would be at 36 inches. If the ratio was 0.66, the ball would be 2/3 of the height. For example, starting at 36 inches, the ball would now be at 24 inches. This graph shows a similar relationship to that of the graph before. As the potential energy increases, the kinetic energy decreases. The potential energy increases to a point where it eventually reaches where the kinetic energy started off at. Since the initial kinetic energy appears to be equal to the final potential energy, this graph shows the law of conservation of energy. The work used to calculate the kinetic and potential energy of the ball of same mass at different heights was very similar to the work used before. For potential energy, the same formula mgh was used, and with kinetic energy, the same kinematic equation v equals v0 plus at was used to find velocity, and velocity was then plugged into 1/2 mv squared.
Now shown is a percent errors for the 3 balls from the different heights. To find the percent error, similar to before, we used the initial potential energy using mgh and compared that to the final kinetic energy using 1/2 mv squared. The potential energy was our theoretical value, and our final kinetic energy was our experimental value. This is because for the potential energy, we have all the values and we know they are accurate. The mass, the gravity, the height. But for the kinetic energy, the value of velocity is impacted by time, which we are trying to test how accurate it is. Our time may be inaccurate. This is why it is our experimental. For the ball dropped at 36 inches, our percent error was 4.62%. For the ball dropped at 24 inches, our percent error was 43.4%, which most likely came from an inaccurate time measured. The times are very small, and they are using velocity, and velocity is squared, so a small impact in time could heavily influence the percent error, which is why that may be so large. And for the ball dropped at 12 inches, the percent error is 8.67%. Some ways we could improve the experimental design is doing more trials, especially for showing from the ball dropped at 24 inches. We did not do enough trials for that, which was the reason why the time was so off, which made the velocity so much smaller, affecting the kinetic energy. Another improvement we can make is expanding our range. Instead of just dropping it from 3 heights at 36, 24, and 12 inches, we could have done more heights, maybe 8 inches apart instead of 12, to further show the ratio of energy to height. Some limitations due to being limited to just household materials include having to use a yardstick like we said before. In an ideal environment, we would have used a much longer stick that was measured in meters, so that way we could drop it from further distances and further differences as well in the height drop to show the relationship between height and energy. Finally, the relationship between our independent variable of height and our dependent variable of energy is that as the height dropped increases, the energy also increases. Thank you for watching our video, and I hope you enjoyed our experiments.